So now that we know what the constituents are in a computer, we're ready to talk about the next question. The next question is, what is an algorithm? In this lesson, we'll answer that question, and we'll also explain what a programming language is and what is the art of programming, what it is that we do when we're actually programming. So the first definition of an algorithm that one can give is that it's a recipe. It's a recipe that's given to achieve a goal or perform a task. Now, an important detail is that this recipe is always given under some specific assumptions. Some specific assumptions on the atomic operations that are available and global constraints on these operations. So in some way, an algorithm is always relative and always ignores some low implementation details. So the most natural analogy that's always given for an algorithm is the analogy of a cookbook. Provided enough details can be filled in, a cooking recipe describes how to get from raw ingredients to a full preparation. So for example, a recipe for lasagna. But if you think about it, a recipe for a lasagna can have a lot of variation in it. For instance, some recipes will tell you to prepare a bechamel sauce, while others will actually tell you how to do that. So some of them will make assumption on some of the background knowledge that you have, or some of the tasks that are sufficiently simple that they don't need to be described. Also, the cookbook recipes usually don't tell you to throw away an ingredient if it's past their due date, but they will tell you which ingredients to buy. So these are the kind of details that some recipes might include, but not some others. In general, cookbook recipes will also ignore some space limitations. For instance, if you have limited kitchen space or few stove stops, they won't tell you what to do in that case. And many cookbook recipes will also ignore time constraints. So you will see that a lot of this analogy carries over to computers. Some computer algorithms will ignore time constraints or space limitations as well. So the next question is, what is a programming language? Well, a programming language is a formalized language that can be used to write source code. And the particular property of source code, I still need to define that, is that source code can be automatically translated into instructions for the CPU. And I remind you that instructions to the CPU is written in assembly code. Let's draw a little diagram to represent this, because this diagram will be useful later. So if I had here my programming language source code, the point is that there would be an automatic translation to assembly code. And if you want, on the left-hand side is language that is closer to human language, or at least that humans have an easier time to read, while on this side is language that's really meant only for the CPU and that no human can really read. So if you want to have the picture, the stuff here is very CPU-like and unfriendly to humans, while the stuff here is very friendly to humans. Okay, so in general, the abstraction goes up as we go from right to left. The abstraction, because you don't need to deal with the particular details of the platform that's being used. Okay, so now I want to talk about the art of programming. An algorithm, I remind you, is a recipe to perform a task given under specific assumptions on atomic operations that are available. Programming language is a formalized language that can be automatically translated into source code. So what is programming? Well, programming in language PL consists of writing down a recipe for the task under the assumption of the operations available in the programming language. Okay, so you have some specific task that is here in the human world, and you have here the CPU, and I remind you of the little picture of data and actions, and this is CPU or assembly code world, right? And the goal is to transfer the task all the way there. Now, we have an intermediate language, which is the programming language PL, and we know that from PL, or from source code in language PL, we can go automatically to assembly code. So programming is precisely this step here, which is the step of translation of the task into the programming language. So this is programming. Okay, so we're taking the task and making some decisions about how to implement things so we can translate the whole task into into source code in that programming language. So this source code in the programming language deals with data and actions at the CPU level. So it also has data and actions. And if you want, here there is also data and actions. And maybe the actions would be translated into formulas at the level of the task if we're doing mathematics. And the data is just some mathematical object. So when doing the programming step, we are translating the objects to data and the formula to actions. Okay, so this is quite important. For instance, we might have an object here which is a polynomial over the integers, and we decide to translate that at the level of that programming language into a list of ints. Okay, so we've made two choices here: to represent the polynomial as a list, to represent the integers as ints. And then we have specific things we want to do with those objects, for instance, compute a derivative, and we translate that into some specific actions at the level of the programming language. Okay, so that's a general description of the art of programming. Now, there are many programming languages. And if you remember, the picture we had was that at this level was assembly code. And actually, so this there for a certain CPU, and actually there is more than one. There is many different types of CPUs, so many different types of assembly code. And all the way here was our abstract task. Okay. But in between, there is this island of source code in a certain programming language that we want to get to from the task. So everything there can be automatically translated to the assembly code. Okay, but actually, this formalized programming language that's sitting in the middle is not an isolated island. There are many different intermediate programming languages that can be used. So one is called machine code, and remember, the abstraction was going up as you go to the left. Okay, so this is very concrete and this is very abstract, your task that you want to perform. And there could be a task in mathematics, a task in some other field, whatever it is. There's many, the abstraction can go in many different directions. But anyway, there are many intermediate programming languages. That was my point. And the first layer on top of assembly code that exists sometimes is called virtual machine, is the layer of virtual machines or machine code. And just like assembly code, there is more than one virtual machine that's possible. But maybe that's a bit vague to you, but let me give you an example. You might have a Nokia phone, or you might have some other brand of phones here, an iPhone or whatever. But if your virtual machine is the virtual machine that Android uses, right? Because there is one virtual machine associated to Android, then that means that you are able to run any program that's any game or anything, any program that's programmed for the Android machine code. So it doesn't really depend on which phone you're actually running. This correspondence here, if you want, is many here for one. And that's the point. The point is that these virtual machines are abstracting over very different architectures on the right. And they give you some intermediate layer between higher level programming languages and very, very low level assembly code. So you could tell a virtual machine, for instance, to wait for a key press. You could ask a virtual machine to print something to the screen, and so on. And you don't have to deal with the level of details that you would have to deal with for the assembly code. Okay, so another layer of abstraction on top is the programming, the general purpose programming languages. So C, C++, or JavaScript, or Python. Now we'll see this a bit later, but there is an automated translation of C, C++ to a variety of assembly codes, and this requires different compilers like GCC. And there is a virtual machine associated to JavaScript. So the path here is more that the JavaScript code can be translated to machine code that can be then automatically translated to several other assembly codes. And for Python, it's kind of the same thing. There's another virtual machine that serves at the interface with several different assembly codes. Okay, and maybe yet another layer that's extremely abstract is the layer of computer algebra systems. So if you are interested in mathematics, you are particularly interested in this layer. So there would be MATLAB and Maple, Mathematica, and maybe Sage. Okay, and each of those come with their own programming language. And essentially, Sage's programming language is the same as Python's. So the two are more or less the same. You can import one from the other and vice versa. Well, those are very specific, and what you're programming here will get translated most of the time into C, C++. Okay? So if you have a certain task, you can decide to hook up with the assembly code here for your particular machine by joining in from the left with any box on the right. And that's the art of programming. And you could pick something very far to the right, but that would be kind of stupid because you would be programming at a very low level of abstraction. Depending on what you do, there is probably a language that exists to do pretty much exactly what you want. So that places itself at just the right level of abstraction to do what you want to do. And so if you have a task that is related to mathematics, the best bet is to either use MATLAB, Maple, Mathematica, or Sage. Now, as I said, Sage is more or less the same as Python. So the goal in this course will be to learn Python, because as a freebie, we'll immediately be able to use Sage. And learning Python has a lot of advantages over learning Mathematica, Maple, or MATLAB, because this is a very general purpose language. So a lot of people use it. There's a lot of documentation online, a lot of help, and a lot of resources to generally learn Python. It will also be more useful, whatever you end up doing afterwards, than learning just a very particular language. So if you learn MATLAB, you are not any better off to learn Maple afterwards than if you had learned Python, for instance. For the general introduction to programming languages. Actually, it's not so general because I've already made some choices about the programming languages that I emphasize. Those are called imperative programming languages. So in the next lesson, I'll really explain what an imperative programming language is and actually also explain what the other programming languages are.